Assalamualaikum and a good day. So today our group will present the ozonation in water for ammonia nitrogen removal. This is a sustainable solution for industrial application. So we are from pHantastic 5, which our group mate is Kishan Kumar, Shahriman, Arif Shazwan, Nur Hashikin and me, Dain. Here is introduction for our project. The selected reactant that we choose is ozone. So background of study, ozone has gained significant attention for its effectiveness in treating ammonia contaminated environment, particularly in industrial and environmental application. The strong oxidizing properties of ozone enable it to react rapidly with ammonia and break it down to harmless byproducts such as nitrogen gas, water and oxygen. So this makes ozone highly efficient and environmentally friendly alternative for ammonia removal compared to conventional chemical treatment. So here's our equation in this project. So for our main reaction, ozone will react with NH3 and will produce nitrogen gas and H2O, which is water. The byproduct is ammonia will react with ozone again and will be nitrogen oxide and H2O and H+. And the other side reaction is nitrogen oxide will react with ozone and will produce NO3 negative and oxygen.
Next, our chosen reactor, the continuous stirred tank reactor or CSTR, and here is why it is the ideal choice for our application. First, enhanced mixing. The CSTR ensures true mixing of ozone gas and water, significantly improving mass transfer and enhancing the contact between ozone and ammonia nitrogen. Second, uniform concentration. The continuous stirring maintains a consistent concentration of ozone throughout the reactor, leading to a stable and predictable reaction rate. Third, high efficiency for homogeneous reaction. CSTR is highly effective for liquid phase reaction like ozonation, maximizing overall reaction efficiency. Additionally, ease of operation. Its simple design allows for easier maintenance and optimization, which is crucial for water treatment process. Finally, cost effectiveness. The straightforward construction of a CSTR reduces both installation and operational costs compared to more complex reactor type. In conclusion, these advantages make the CSTR the most suitable and efficient choice for our project.
So for the synthesis route, first we would prepare NH4Cl solution. So for that we need to first dissolve ammonium chloride in distilled water to make a solution with an initial concentration of 50 mg per liter, and then we need to ensure a total volume of 200 ml for the reaction. Second, we need to adjust the pH, so use 2 molar NaOH to adjust the pH of the solution to 9.0, as a higher pH enhances the reaction rate of ammonia with ozone. Second, we need to prepare the catalyst. So weigh 1 gram per liter of the selected catalyst with CTAB nickel oxide in slurry form. Second, for the reactor setup, we need to set up a 250 ml CSTR reactor for the reaction, and we need to place 200 ml NH4Cl solution in the reactor. And for the ozone supply, we use. Okay, for the next slide of synthesis route, this experiment should be conducted at certain reaction conditions. The experiment should be performed at room temperature, which is 25 degrees Celsius, and 1 atmospheric pressure for 120 minutes. With the catalyst CTAB nickel oxide and other conditions, NH4+, which is ammonium removal rate, is 95.93%, and gaseous nitrogen selectivity is 80.98%. At the end of the reaction, nitrogen gas and water with remaining ammonium ions, nitrates and nitrites would be pumped to cyclone separator. Cyclone separator would separate nitrogen gas and ozone gas from the water stream, and then the water stream would pass through denitrification tank. Remaining ammonium ions would be converted into nitrites, and nitrites would be oxidized into nitrates into the nitrification tank, also known as aerobic tank. and nitrates would be reduced to nitrites, and from nitrites to nitric oxide, and from nitric oxide to nitrous oxide to finally nitrogen gas in a denitrification tank with the help of denitrifying bacteria. For the gas separation, ozone destructor, the excess ozone gas and nitrogen gas would pass through ozone destructor. Nothing would happen to the nitrogen gas because since nitrogen gas is an inert gas, and ozone would be converted into oxygen. And using the membrane separator, oxygen gas would be separated from nitrogen gas. Nitrogen gas would be vented out, and oxygen would be stored for other purposes. And this is the PFD diagram of our ChemE Cube mini plant. And this is the PFD diagram of our So this is our first explored PFD diagram. This PFD diagram was rejected and wasn't finalized because we did not implement a treatment plan for excess ozone gas. Ozone gas is highly reactive and it's very harmful to the environment. Thus, before being released into the environment, the ozone gas have to undergo a treatment plan where it should go pass through ozone destructor, so the excess ozone gas can be transformed into oxygen, and then oxygen can be vented out or can be stored. And since this PFD diagram did not include any treatment plan for oxygen excess ozone gas, so this explored PFD diagram was rejected and wasn't finalized. And this is our second explored PFD diagram. This was rejected because we did not include any catalyst addition in this PFD diagram. This PFD diagram shares some similarities with the first one, and both of this PFD diagram did not include the addition of catalyst. So without the catalyst, the conversion rate of ammonia would be very much lesser than we expected, and the productivity of nitrogen gas would be less also than we expected. Hence, this PFD diagram was rejected and wasn't finalized. And this is our second explored PFD diagram. This was rejected because we did not include any catalyst addition in this PFD diagram. This PFD diagram shares some similarities with the first one, and both. And now we can look at the dimension of our ChemE Cube mini plant. So this whole cube, the dimension is 1 foot by 1 foot by 1 foot, which is 30.48 cm. And this is the entire 360 3D view of our ChemE Cube mini plant. And this is the entire 360 3D view of our ChemE Cube and in this slide we can see the dimension of centrifugal pump, ozone destructor, CSTR, cyclone separator, heat exchanger, and denitrification tank in our ChemE Cube mini plant.
This slide covers the red law for two reactions involving ammonia and ozone. In the first reaction, ozone reacts with ammonia to produce nitrogen and water. The red law expression is shown with rate constant K equal to 1000. The second reaction involving ammonia, ozone and producing nitrites ion, water and hydrogen ions. It has red law with a rate constant K equal to 100. We use this expression to calculate the rate of desired and undesired product. We assuming the reaction in second order since the unit for rate constant is per molarity second. Next, the calculation for the third reaction, yield and selectivity. The third reaction where ozone react with nitrites ion to form nitrates ion and oxygen. The rate law is defined with a rate constant K equal to 10. Then we calculate the selectivity using given formula. It is the ratio of desired to undesired product rate, while yield is the fraction of the desired product rate to the total rate. Last but not least, for the calculation part, we look at the volume and space-time calculation. For our reaction system, the initial concentration and volume of the ozone is input by the user. Additionally, space-time calculation or tau is determined using the ratio of reactor volume to volumetric flow rate. This calculation ensure proper reactor design and efficient processing.
Okay, now we're gonna discuss about the MATLAB programming. So from the coding that we create to calculate the tau, selectivity, and the percentage yield. So we need the user to key in the input, which is the NH3 concentration, the ozone concentration, and the NO2 minus concentration. So from the user input, so the programming or the MATLAB will calculate the percentage yield, tau, and the selectivity.
Four impacts that we want to highlight in this project, which are SDG 7, 9, 12, and also 13. For SDG 7, which is affordable and clean energy, we will reduce energy consumption by improving reaction efficiency, and we also minimize the needs for high energy traditional reaction process in electrification. Second, SDG 9, which is industry innovation and infrastructure, as we promote innovative use the ozone technology in industrial wastewater treatment. We also encourage sustainable infrastructure for cleaner industrial process. And third, SDG 12, which is responsible consumption and production, as we will support resource efficiency by reducing nitrogen-based waste and emissions, and we also promote circular economic practice by transforming wastewater into reusable clean water. And we also minimize environmental harm through a responsible treatment process. And lastly, 13, which is climate change. This is because we reduce the nitrogen emission that contributes to environmental pollution, and it will mitigate the impact of harmful gases of climate change by reducing nitrogen loading in ecosystem. So, as a conclusion, ozone-based certification provides a sustainable, energy-efficient solution for ammonia removal, and is also aligned with SDG 7, 9, 12, and 13 as I mentioned earlier, and it also offers industry a practical approach to reducing environmental impact and achieving sustainability goals. This is all the reference that we refer to completing this project, and that's all from us. Thank you for your attention. Thank you.